Okay, so hi everyone and welcome to BrainMap. It's my great pleasure to introduce our speaker today, Dr. Simone Winkler. Dr. Winkler is a Stanford trained and NIH K99 assistant professor at Weill Cornell Medicine. Her research focuses on ultra-high field MRI and multidisciplinary engineering applied to medicine and medical imaging. I would just like to remind our audience to please address any question you have using the Q&A box. Dr. Winkler, thank you very much for coming here today. The virtual stage is all yours.
Thank you so much. I'm really excited to be with you today, even though it's virtual. I visited Harvard or the Martinos Center as a postdoc in 2014 for some short COIL work. So it's very exciting to give a talk with you today. All right, so I've been faculty for a little while now, not very long. So this is my lab, and we have 3 postdocs, Eliza, Isabel, and Saeem. I'm very excited to work with them because they're really wonderful. Despite COVID, they've been working so hard and been so productive. We have several papers submitted and a patent and 3 grants and so on. And they only arrived in early 2020. So this is really more than I could ever wish for. Here's one of the very few outings we were able to do despite COVID, outdoors on my roof. Yeah, so that gives you a bit of an idea about who we are. So let's start with the science. So I submitted a K99 award many years ago by now. And what I proposed was to build advanced hardware or technology for ultra high field MRI, and in particular for use in the Human Connectome project. So today I'll be talking about hardware a lot. Maybe that's a little different from other seminars in this series, as I've seen. So I hope it's exciting, and I hope it's not too difficult to understand. I'll briefly introduce ultra high field MRI, and then I'll explain 4 major engineering related challenges related to ultra high field MRI, and actually in particular applicable to the Human Connectome project. The first one will be image shading because of B1 inhomogeneities. The second one is related to B0 inhomogeneities and the distortion it creates. The third one is related to MR safety and SAR. The fourth one is a bit of an older work, which is on acoustics, but because we deal with gradient strengths in the Connectome project, I thought I'd insert it here. And then more recent work is on flexible and stretchable coils. That's mostly what my postdocs work on, and that's super exciting as well. And I think it's applicable to any field strength because SNR can be improved so much with these coils. All right, so just to give you a recap or a quick outline about my grant, I got the K99 award in 2017, and I'm soon going to be in the last year, so that's exciting. The idea of the Human Connectome project is probably familiar to you given this seminar series, but what I'm proposing here is to build high-end MR instrumentation. In my grant, I proposed to use it for neurodegenerative disease, but it can be applied to a wide array of things. So let's start with the hardware. This is a scanner cutaway, and most of you probably know this, but there are 3 main system components. The big one is the magnet, so that's really what the bulk of all of this is. It's this big cylinder here, and this is the device that creates the 3 Tesla or 7 Tesla or any other field strength that is used in MRI. And the 2 that I will mostly talk about today are the RF coil and the gradient coil. So the RF coil is located right behind the bore wall here. It's used to excite and receive the RF signal. And then the gradient coil is just behind that, and that is used to localize where in the body the signal is either excited or coming from. But I'll leave it at that because you probably know most of this. Typical field strengths clinically nowadays are 1.5 to 3 Tesla. There's some FDA approval for 7 Tesla, but only for certain anatomies, coils, sequences. So we still have some work to do. All right, so why do we even use ultra high field MRI? This is not an entirely fair comparison because on the right we have histology and on the left an in vivo image, but just to get the point across, we get a lot better signal, and one way to use that is to increase the resolution of the image. The reason for that is that as the field strength goes up, the energy gap increases, and so we can use that for higher sensitivity, SNR, that kind of thing. So yeah, I am showing the Stanford scanner here because our Cornell scanner is delayed due to COVID. It's already situated in Milwaukee at GE, and they would love to get rid of it, but we don't have a building because it fell through during COVID. So Manhattan's always a bit of a problem with real estate, so we're struggling to get that sorted. I hope it happens soon, but you get the idea. It's a big scanner, a little bit bigger than what you're used to for 3T perhaps, because of the added engineering complexity. It's not fully FDA approved. As I said, there's some FDA approval nowadays, but we're still working on getting that to its full stages. There are not that many in the world. I think this number might be slightly outdated. It's probably over 100 now, but it's still not that common. Okay, so that brings me to the 4 challenges that I would like to discuss today. The first one is B1 inhomogeneities. And what that does is it causes image shading. I'll go into more detail in a later slide, but you can see here as you go up in field strength, you start to get dark and bright spots. And obviously radiologists aren't too happy to see that because, it's hard to diagnose something, or you could even think that the dark spots are a disease in some cases. So that's not a good thing, and we want to mitigate it. The second topic is safety. So this is the same effect that happens when you use a cell phone. Basically, the RF energy that is emitted by the MRI scanner or the cell phone is deposited in tissue and causes heating. And obviously, that's not something you want because you could damage tissue that way. So that's something I will discuss as well. The third one, I'll just briefly touch on it. It's B0 inhomogeneities. The field, the 7 Tesla or 3 Tesla field has to be highly homogeneous. Otherwise, you get distortions and other not so great effects. I'm mentioning this briefly because that's what I worked on a little bit when I was at the Martinos Center. But most of the work is really done by Jason. So I will just touch on it because it's important for ultra high field MRI and of course the Human Connectome project. The fourth one is related to gradients. As we go up in gradient strength and currents, we start to have a lot of problems related to vibrations and acoustics. This is particularly relevant to the Connectome project as you do a lot of diffusion, need higher gradient strengths. Yeah, and so I'll show vibrations and acoustics and a little bit of thermal work too, because obviously that requires cooling as well. So let's start with the first one, the image shading. So the challenge here is that as you go up in field strength, not only does the magnetic field strength go up, but the Larmor frequency is directly proportional to the field strength. So at 3T, you might have 128 megahertz, but at 7T, you're actually on the order of 300 megahertz. And what that means is that the wavelength in tissue shortens dramatically. So you're now on the order of maybe 13 or so centimeters in tissue for the wavelength. And that means that, a minimum or a maximum of a wave can occur, just inside the head, for example. And that's why you see here a minimum as a dark spot, a maximum as a bright spot, and so on. If you look at this in a different way in the ideal magnetic resonance, experiment. What you want is a circularly polarized signal for the B1 field. But as you load it with tissue, you actually deviate from the circular polarization. You get elliptical polarization and linear polarization, even in some cases. And on one hand, that causes signal loss, and on the other, phase shifts and all kinds of complicated things. So what people do to remedy this is popularly recently is parallel transmission. So you don't just excite from two channels as in the quadrature case that's used at lower field strengths, but you actually have more channels and you have different pulse signal shapes even per channel. RF-SHIMMING is a simplified form of that. It does the same thing, but instead of changing the signal shapes, it only varies the amplitude and phase. And then one other fun thing here is dielectric shimming. It's actually gaining a lot of popularity. I worked on it long ago, but since then, a lot of people have been picking up this work and doing more in it. So it's exciting to see. What you can do here is passively perturb electric and magnetic field lines by inserting materials with high permittivity into the bore near the anatomy. All right, so that brings me to the first research topic in this area. This is very, very recent. So one of my postdocs, Saim, started working on this project. There is actually no 7T body coil. All the 3D scanners and 1.5 Tesla scanners, they usually have a vendor built-in body coil. It's really versatile. Clinicians love it because you make this homogeneous excitation field, and then you can use local surface coils to receive that. So what the problem here is that, that the reason such a thing does not exist is because at 7 Tesla or higher, the wavelength effects become so significant. As we said, in tissue, the wavelength is 13 centimeters. It's a bit longer out of tissue. So you can't really use birdcage coils anymore at that size. You still use it for head dimensions, but not for body dimensions. And another aspect here is that the coils are limited in length because of these wavelength effects. So, Tommy Wan came up with the TM coil a while ago, so that one is very nice. This would be the birdcage if it were functional at 7T. And in our design here is that we mitigate this wavelength problem by introducing a second dimension. So basically, instead of having a 1D rung here, we have something like a 2D rung, right? And not only allows us to, allows that to control the currents and hence the B fields in this dimension, in the SI dimension, it also allows us to create coils that are long. And that's really interesting, because sometimes you need whole body applications, and it could open a lot of avenues. So our results are shown here. We compare it to the TEM coil by Tommy Wan and the birdcage coil. So this is the short version. So usually the birdcage at this dimension would be 33 centimeters long. At the 33 centimeter length, the TM coil still works fairly well. We call it CHPL coil for cylindrical high pass ladder, works well also. But as soon as you go to the 91 centimeter length that we simulated here, both the TM and the birdcage fall apart. And our coil, even though with a little less average signal here, still works very nicely at that length. So this is a quick plot of the imaging mode. I think this is 4-channel drive. It might be 8-channel. I'm not entirely sure now, but just to explain that, it's a multi-channel drive. And then we did a very simple test as a first test, because this is early work, with a quadrature prototype. And the images shown here, at first glance, you might think, well, this is not good. There's a null here or signal loss. But when you think about it in quadrature mode, the wavelength around the body coil is actually comparable to the circumference of the coil. So it's normal to have signal fall off here in quadrature mode. So this agrees nicely, and now we're working on an 8-channel prototype and hopefully soon some in vivo results, given the fact that we don't have the scanner here yet. But yeah, and V1 homogeneity improved by a lot, and actually also SAR is improved, which is a good result. So the next one is a fairly old design. I just wanted to bring it up because it's interesting what kinds of coils you can think of at 7T. Here we, with Ricardo Starra, a few years ago, we made a 2-row head coil, 16 channels. It can either be driven by using a single row or a checkerboard, or you can drive all 16 with Butler matrices. So that was really cool. And in order to avoid inter-element coupling, he came up with this shield around each element. So that helped a lot too. Yeah, and the Z segmentation with the rows helps you to get a little bit of control in the SI direction as well. So that's a little bit similar to our body coil design, but not really. So the third one, I will only touch on this briefly. That's what I mentioned with dielectric shimming. I worked on this several years ago. I wasn't excited when someone told me, well, you'll just take this dielectric pad and put it somewhere and then you'll see what happens. I don't know, that's not my thing. So I tried to come up with some theory and describe how to put these how to place these pads and what material to use. I used the Maxwell equation in spherical harmonic form and decomposed it into some parameters. And then we were actually able to find an optimized situation here where not only the average signal is higher, but the homogeneity is improved as well. So I think that concludes the V1 and image shading. The second quadrant, I guess, is the V0 inhomogeneities. And this is mostly work that Jason did. I did work with him a little bit. So because the talk is at Martinos, I thought I'd show some of it. You probably know most of these things already. So the reason why this is so important is the B0 field has to be extremely homogeneous. So I think it's on the order of parts per million, on the order of 0.25 microtesla for 7T, which is, that's a pretty large dynamic range, which always requires a lot of engineering finesse. And spatial encoding depends on this homogeneity. So if you don't do this right, your image will show anatomies in a different place as compared to where they are in reality. And of course, there's also signal loss related to it. The sources for this inhomogeneity is, on one hand, the magnet construction. This is just inherent to the magnet, and it's actually mostly corrected when the magnet is sighted. I'll talk about this over here. But what's really more of a problem is the body itself. So air and water have different susceptibility. One is diamagnetic, the other is paramagnetic. And the air cavities in the body cause a lot of problem in that sense, because tissue is mostly water-based, and of course the air would have a different susceptibility. So you can see here that, a very, very rudimentary simulation that I quickly did is having some air gaps here in this head and and see how the field gets distorted. And even just this very quick thing that I did showed you that there is some significant shift in the magnetic field. So in order to remedy this situation, there is a passive approach that corrects for magnet construction. So when a magnet is sighted, they have little rails. They put these little iron inserts into the rails. It seems a bit like black magic, but they figure it out mostly, which I'm always impressed by. But when it comes to the in vivo situation with the patient-dependent susceptibility differences, you use actual coils that correct for these. Traditionally, people or vendors have used spherical harmonic coils. So because this volume of interest is spherical, it's easy to decompose that into spherical harmonics. And it's easy to build coils that act on one specific harmonic. So this is, I think that's the second order and so on. I don't know exactly, but yeah. And then recently, maybe the last few years, people have worked on matrix shims, and that's where Martinos comes in more. What you do here is, in order to get better control at even higher orders of spherical harmonics, you use a lot of little loops. They all have a DC current on them because that can be used to generate a static magnetic field component, right? And then as you weight the sums of all these little fields the right way, you might be able to correct your fields. So historically, Yale made this first prototype here where they had multi-turn coil elements, and then they had a separate RF coil that was located at the outside. And the problem was that actually this shim coil shielded off a lot of the signal that came from the RF coil. So they made a gap here, but still maybe not so ideal. So then Duke came up with a cool idea where the RF current and the DC current run on the same loop elements here. And that, can be more complex, but it allows for a lot of nice things to solve this problem. And it also solves the interaction with the RF coil that Yale had to face. And then Jason Stockman, who's probably listening, made this very, very cool coil that I'm still in awe of. So what he did was, this is the conventional RF coil element with only the RF path. And then in order to allow for DC to flow, each of the capacitors in this coil has a choke above, or, in parallel to it, so that you can have a DC path. And he made this very cool helmet that, allows you to have a very nice receive signal and increased SNR. So when I briefly visited Martinos in, I think it was 2014 in summer, it was probably one of the best summers of my life because I was with you guys. I just tried a few new things. It wasn't, earth-shattering, but I thought I'd show it because I enjoyed my time so much. So I tried a coaxial loop element just to separate out these two conductors and decrease the complexity, because as you go up to 70, you might need even more of these chokes because there are more capacitors, and then it starts to get a little bit messy. So that's what we tried here. We had the inner conductor running the DC current for the shimming, and the outer conductor has the RF current, just like a normal receive coil. And then we did the same thing with a concentric loop element. The inner one was DC and the outer one was RF. So that allows you to have a reduced number of capacitors and chokes as well. These were the results, and it works fairly well. It could work better, but it was a nice study. I left the lab I was in after that, so I didn't continue much on this work, but I followed Jason's work a lot, so that's exciting. And with Saeem, we were discussing to maybe work on shimming again, so that might happen. We're not sure yet. All right, that brings us to the third quadrant, which is MR safety. So I'll explain more in detail in the next slide. So the challenge here is that you have RF power from this RFV1 signal deposited in tissue. This is measured most commonly as the specific absorption rate. The reason this is a concern is because, obviously what that does is it heats up the tissue, right? And if you make a very brute comparison, that's the same thing as a microwave oven. That's what a microwave oven does, just at much, much higher powers. And so you don't want that, right? You don't want to damage or cook any tissue. So there are two main metrics. The first one is the global SAR. That would be the RF power deposition over the entire anatomy of interest. That one's actually easy to measure. It's, you can just measure the reflected power and you get a sense of this global SAR. But what's really a problem at these higher fields is the local SAR, because we have local variation of SAR that comes from the wavelength effects, right? In the same way we had the maxima and minima for the B1, the RF field, we have maxima and minima for the SAR field as well. And you can see in this little image here that, you could, without realizing, you could cook someone's tiny little area of the brain here and really cause problems. At low field, this isn't such a big deal. So people at 3T didn't worry about this as much because, the wavelengths are longer. And so this local effect is less of a problem. But at high field, not only do you have these local effects, but moreover, because SAR is a power measure, it increases with the square of the field strength. So if we go from 3 to 7T, that's, I think, a factor of 2.3, and then you would get the square of that alone in the average SAR. So, that's like 5 or 6, I don't remember exactly. So that's a lot just because we try a new field strength. But then moreover, we have variation in fields and also tissue properties. So this can lead to very strong variations in local SAR. But what's more complicated is actually that you can't really predict this. It changes based on the patient, based on the coil, based on the position. There are so many different aspects that go into it, and one simulation alone will not tell you much. So it's a hard problem. If you use PTX, you might even further cause more problems, because you could have worst case constructive interference of electrical fields and therefore SAR. So that could be a big problem. So to date, there's really not an experimental procedure to measure local SAR. But what people have done is SAR minimized pulse design. I will show some about that. Then you could also find methods to experimentally measure this local SAR. I will show some of my work on that. One thing I did in the last year is to predict it with machine learning. And alternatively, you could focus more on the temperature. And some people, like Tommy Wan, argue that that might be the more reasonable metric anyway, because it's closer to physiology. But so far, we're still working with SAR in regulatory limits. So let me show the SAR minimized pulse design. This is work by Mihir Penza at Stanford, and by now he has graduated, so he did some really great work. What he uses here is basically an offline catalog as a SAR database. It's all based on EM simulations in Sim4Life, and you develop these compressed sets of SAR images or SAR maps. And then when you are at the scanner in real time, you use your localizer and pull one of these data sets that matches the patient most closely. And then you incorporate that into your RF pulse design. In order to make a PTX pulse design that does take SAR into account and doesn't cause any major problems. So the results are shown here. This would be the birdcage mode with no PTX pulse design, so the flip angle isn't homogeneous. Then you'd use a standard SAR unaware pulse design where you do get your flip angle homogenized. But the SAR here, you can see, is actually a problem. And now using his technique called impulse, he actually does both. Flip angle is homogeneous and also the SAR is low. So it's exciting. Now, something I worked on a lot, and we're actually picking this back up with my postdocs, is the thermoacoustic SAR concept. So what is it? I mean, I love this. I love multiphysics, anything that's not just RF and where you have other physics, I just jump right at it. So here you go. There's the word acoustic in it. So that was super exciting for me. If the thermoacoustic effect is basically, some people call it microwave hearing. It's more of an old school term, but maybe you've heard it. You have a pulsed RF energy source here, right? And then this RF energy hits an absorber, so that absorber heats up instantaneously, therefore expands instantaneously, and therefore instantaneously causes a pressure rise at the boundary. Now, if you do this right, you can create a pressure wave that is exactly an ultrasound signal, right? And then at the boundary of the tissue, you can pick that up with an ultrasound transducer. So that's the thermoacoustic effect. And then I realized that the absorbed RF energy is, of course, exactly the SAR, right? So if you use the RF coil as a transmitter, it would be ideal. It generates the same local SAR pattern as in an MRI scan. And, you know, then you can put a few ultrasound transducers around the head and measure the ultrasound signal. This is the wave equation. You can see if you do this right, SAR is a direct excitation term to the pressure wave. So some first modeling showed that this works. We had original SAR patterns, ran them through the wave equation and reconstructed it. I think that was 16 ultrasound transducers. This was only a 2D example, but you know, obviously very early work back in the day, and it shows that this matches fairly well. Of course, there's room for improvement, but the reconstruction was very, very simple, and everything was just a basic feasibility study. So yeah. All right, and then we tested it in an experiment. We have had a thermoacoustic imaging platform at Stanford with this company called Entra. They're super exciting and helped us a lot with this project. It has, you know, an ultrasound transducer here and 2 RF horns to generate an E field. Yeah, and so in order to mimic our problem here, we varied the SAR by varying the conductivity and the E field, so that, you know, our simple experiment, that's how we tried to mimic varying SAR. So the conductivity was varied by making a phantom with different saline tubes, and then the E field was varied by turning one of the horns off. And you can see here what the results were. So this is the reference test where SAR is basically the same everywhere. And then this is where the SAR is varied. It looks different because the above is actually made more inhomogeneous by rotating the sample. Whereas here we turn that off, so you have a different azimuthal and radial resolution and so on. So yeah, and I don't want to bore you with the details, but it worked reasonably well. And we actually work on, you know, making this more of an actual MR experiment now in future work with my postdoc Isabel. All right. So in order to integrate that into the scanner, you need to do a few things. It's not too bad. You need a fast rise time for this. So, you know, you might just use a different signal generator. The power might be good enough. I did a first, you know, estimation, and it might work out. You could start with easy anatomies that don't have the skull aberration, for example, the abdomen or the knee. And for the brain, you know, actually our bandwidths are pretty low, so this might even work in terms of penetration of the skull bones. And we can also mount the ultrasound transducers at the lateral acoustic windows. All right, so this is the last project on safety and SAR. This is recent work by myself. Now my postdoc Saim started working on it, so you'll hear more from him about this. I call it AMR safe. It's real-time prediction of local SAR using deep learning. So you have as the input an anatomical image, and then you have a unit deep learning network, and the output is a SAR map. This anatomical image is not really an MRI image in this, in this first test, because we wanted to, be sure that both are aligned, and we're working on the real image as the next step. And so the results are shown here in brief. At 3T, that's the first two columns. We have one position here where you have the head and shoulders. This is the input image, and then this is the simulated SAR, so that's the ground truth. And what we predict here in our very first study is, it's matching fairly well if you compare the two. There's a different position here where you see more of the chest and abdomen. Ground truth is shown here, and predicted SAR is shown here. They are a little bit different from the above still, so that's something we're working on now. At 70, I used just a head coil for the SAR simulation, so only the head was looked at, and you can see the predicted images here as compared to the ground truth. There was some alignment problem that we have since figured out, so there's a bit of blurriness, and this is simply another position showing the neck. So this is working out really well so far for a very first test, and we hope to produce more of this, in the upcoming months. This is some very, very quick sidestep on a project I did at the end of my time at Stanford. Greg Scott and Kelly Byron worked on wireless MRI, and in particular on how to power up the wireless receive coil. So what you do here is you have a primary coil that's connected to the power source, and then by way of induction, the power goes to the secondary coil that is connected to the receive array. And they just wanted to see if it's safe, So that's how you see where SAR and safety comes in. It turns out it's safe, but it's, always important to study safety in simulation a lot. So I don't want to waste too much time on this, but you can see as the two coils are directly above one another, a lot of energy is transferred, so the SAR is low. As the coils are more adjacent, more of the energy goes into the body, but both situations are safe. This brings me to the last quadrant. That would be about the gradients. So let's see here. We worked on this mostly with Robarts in Canada. And so I want to mention a few things about gradients. Most scanners, I think every scanner, I'm not entirely sure, but really the majority of scanners have a built-in body gradient coil. It's, it covers most of the body dimensions. It has a large linear region, but it's not very strong and has a low slew rate. So it's versatile, but not very strong. So some people have been working on head gradient specific designs. It's the same thing, but it goes into the bore as you see here, and you just put your head in there, and it doesn't really work on other anatomies as much. What it does is it gives you a higher slew rate, higher gradient strengths, but it also, and of course, this is important for the Human Connectome project because you want, for diffusion, you kind of want these things. But what it does, it vibrates more and it's louder. So we looked into that. So, I mean, you probably know most of this, but the reason why an MRI scanner is so loud is that you have a very strong magnetic field, right? And you have currents on conductors in this magnetic field. So the Lorentz force is directly related to those two. And so that means you get time varying Lorentz forces, and of course that means vibrations. So in turn, that means your bore wall of the gradient coil here vibrates, and that means it excites a sound wave in the air cavity inside the gradient coil. Now, I always show this slide because it's colorful and wakes people up a bit, because my talks are long, you know. So, and you can quantify these vibrations by causing or creating a weighted sum of different modes. There are breathing modes, bending modes, ovaling modes, and so on. And you know, the average displacement for 3T and 50 amps, that's more of a versatile coil, not so much the head gradient coil, is about 1 micron. One really important thing here is that you can have a very bad situation going on when the two couple. So when you have a vibration at a certain mode and a certain frequency, and then you have an acoustic mode at a certain mode shape and frequency, you can get coupling between the two. It's kind of like the soldiers walking on the bridge in unison, and you know, the bridge collapses. And that can cause a lot of trouble, very loud operation, and potentially damage. So that's where analysis is really helpful. So what we did was we did very extensive modeling that hadn't really been done very much. And I'm not saying that people didn't want to. It's mostly because computational power just wasn't there. You know, we really benefit from this nowadays. We could just put so much stuff into COMSOL and it comes back with these great results. So we're lucky. So what we did here was we had the hard acoustic boundary mimicking the bore wall. We had the head insert gradient here with accurate wire patterns. This is the Z gradient axis, just to make it simple in this illustration. Yeah, and we also had the surrounding air, because that proved important, that you model what's coming out of the bore. And it mimics infinite space with a perfectly matched layer. You can see here that the Lorentz forces are, you know, they vary because of the orientation of the current traces. And then here's an example of what the wave propagation looks like. So you can really see that it's a bit of a mix between a resonance and, you know, traveling wave. So, you know, that was interesting to me. And you can see here as the wave comes out of the bore, it travels outside. So the new things we introduced here was accurate wire patterns, the realistic bore shape, acoustic propagation. And one more thing was the Lorentz damping. So I'll show that in the next slide. The results were really promising. We got very similar sound pressure levels for simulation and experiment. The Z gradient was a bit different because this had hollow copper conductors, and I didn't model that because it took a long time to solve, or wasn't possible with limited memory. But this agreement is pretty good, you know, compared to what was out there in literature. So that was exciting. So the Lorentz damping that we found, I don't want to spend too much time on it, but one thing that wasn't discussed in literature was that if you have a current flowing in an external magnetic field, it means you get this Lorentz force, right? I said that before. And now that means the conductor moves. So now this movement has an effect on this force and the current, because a moving conductor has an induced countercurrent. And so, you know, you have the original current, the induced countercurrent, and that means an induced counter Lorentz force. So in a way, that's damping, right? And so the total force is actually this term. And what's interesting is that it is related to the square of the field strength. So as field strength goes up, I get more damping. So maybe it doesn't get much louder at 70. So here's a little bit of a summary. We talked about Lorentz damping. Here you can see what that actually means. The accelerations go down by a lot when you include the damping term. Same here. If you don't use Lorentz damping, you get the usual 6 dB or not 6, but you know, when you go by a factor of 2.3, you get a certain number of dB and so on. You would get an exactly linear increase. But if you increase Lorentz damping, it actually stays fairly similar, which, you know, that was interesting. And then in order to mitigate the sound, we've worked on some simulation strategies as well. One way of many was to cast the bore walls in ceramic, and that actually reduced the sound pressure levels by 30 dB. So that was good. That was also at a point when I left the lab, so I stopped working on that project at this point. Here's one last slide just on thermal simulations, because these gradients get so hot. So you have water flowing through the gradient conductors. And you can see just a study here for safety reasons. What if the flow stops? What happens? And we can see that actually it gets really hot. This is the bore wall, I guess, unwrapped, this picture here. So you can see it gets pretty hot, on the order of 60 degrees Celsius, which could be a patient concern and could also damage the coil. So this is the conclusion for the first part. There's a little bit of recent work in the next few minutes. Don't worry, it's not too long. So we know that ultra high field MRI is great. It increases SNR and other things. There are technical challenges that are faced, and I talked about these 4 challenges here. And we see that multi-physics simulations and engineering are really essential to ultra high field MRI. So let me follow up with recent work. We work a lot on flexible and even stretchable coils. The problem with common commercial RF receive coils is that they're rigid and inflexible. They're often far from the body because they have to match or fit so many different anatomies. And so, you know, the available SNR is pretty suboptimal, right? And of course, that means the resolution is also limited. Yeah, so then what we want is form-fitting flexibility, right? And ideally, of course, also stretchability. So we'll show you some of that. That gives you better resolution, and you know, you can do dynamic imaging and also increase patient comfort. Of course, you know, this guy looks really happy here with the lady and the, the form-fitting coil. So I think we're on the right track. So this was when I still worked at Stanford. Berkeley built a really nice screen printed coil. The conductors are printed on fabric, and this is used for pediatric patients. So most importantly, the fabric had dinosaurs. That was, you know, what the children like most. The reason they worked on this or built this coil was that when you have a baby or that needs to be anesthetized in the scanner because they would otherwise not stay still, or, you know, other reasons, there is so much monitoring equipment. And then even at Stanford, we only had this adult-sized cardiac array. So this baby is completely buried, and you don't even use all the elements. And it's just not great. So here we are with this smaller, lightweight coil. And I did a first clinical pilot study. I love doing this because I don't spend that much time in the clinic. And, you know, seeing these kids suffer through these MRI scans, that was something, you know, that really motivated me to produce good technology. We did a caregiver survey, and it showed good acceptance of this coil with 4 out of 5. The diagnostic quality was great. All cases were diagnostic. This is a 4D flow image of a 5-year-old girl. And the image SNR was increased as well because the coil is closer to the anatomy. And then the next one is actually exciting because that's a new project that my postdoc Eliza is working on. So not only do we want bendability, we also want stretchability, right? So what we are working on is liquid metal coils, because when you want to stretch coils, of course, you can't do that with a rigid wire, you know, it doesn't stretch or it breaks. So when you use liquid wires, in quotes, they will flow to keep flowing and your conductor stays intact. And in order to make the substrate for this liquid metal stretchable, we use a polymer matrix, and that's soft and, you know, actually very elastic. And then one problem actually is, you stretch this coil, right? That means the conductor is longer, the inductance goes up. So now the resonance shifts. So what we do here is we use an interdigital capacitor. And when you stretch that capacitor, it changes its capacitance to keep the resonance frequency, at the frequency you want. And we show some results here. This is at 3T. So the blue curve is the conventional coil without the self-tuning interdigital capacitor. The red curve is has this self-tuning capability, and we stay within 0.5 megahertz here. And then we have some really cool videos here. This is the fabricated prototype coil. It's molded on this pink surface. So the pink part is actually not part of the coil. It's just the mold. And then the video here, I hope it works, shows you how ELISA stretches the coil. You can see it stays conducting without any interruptions. So it's very cool. Then we did in vitro stretch tests. We put the coil here on a phantom. You see the coil in this case because as we didn't think about that, the coil needs to be doped with something to be invisible. But in this case, it's good because in the image, you see how it's stretched. So if you look at this, see here, you see this coil being stretched, and the signal in SNR stays practically the same. And then this is our first in vivo knee image. We have some artifact here that we're working on. And also here, this is the unstretched position, and you stretch it, and the SNR is very similar. So this is working very well. And the second flexible coil project that I'm going to show here, and that's actually the last slide, is a flexible coil for MR-guided focused ultrasound. So focused ultrasound, you probably all know this, but it's a non-invasive treatment modality where you use acoustic energy to produce ablation or sometimes just modulation. And you use MRI to localize your target. But the challenge is that the imaging quality is so poor because people use the body coil. You have this transducer helmet around your head, so you can't use the head coil, right? And then, of course, that transducer has a shield. So now the RF energy just can't really come through, and it's basically a disaster, if you ask me. So you get these dark bands and very low signal, and it's really not great. So what Isabel came up with here is an 8-channel surface receive coil based on GE's air technology. It's acoustically transparent. Not going to say much about this, but we did a lot of work to prove that. It's very thin and lightweight and so on. And you can even place it in between the water and the transducer with some waterproofing material. Here are some simulations. So you can see here the body coil has really vastly reduced signal, and then with our coil here you get a lot more B1. So we get about 5 without the transducer and a little less with the transducer, and of course no black band artifact. And then in vivo we have some nice images here. This is just the coil, no transducer. The body coil gives a very noisy image, and our coil gives an increase of 7.3. And then with the transducer, so now that's the new coil and also the helmet around it, you get a 7.6 SNR increase. The black band is moved a little bit here. This is actually probably has room for improvement because in order to mimic our situation here, we had some water bags around the around the head, so that was easier to do than to fill the whole transducer with water and potentially damage something. But we're working on the real experiment. It's also early work, so that worked really well, and we also got an increase of scan time by a factor of 2. Yeah, so that was it. I hope I didn't speak too long. I have a ton of collaborators to thank at Cornell, at HSS, of course at MGH for the earlier work. GE is always super helpful. They help us so much with everything. There are lots of people at Stanford for my past work, and Berkeley, and then some people at Utrecht, Andra and Roberts. So thank you so much for letting me speak today. It was really, really exciting. And I guess I can answer questions now.
Great, Dr. Winkler, thank you so much for this great talk. And our first question is going to come from Said. Can you please unmute?
Yeah, sure. Do you have my voice?
Yeah, we can hear you.
Okay, perfect. Okay, first of all, the presentation was very interesting, thorough, and smooth. Thanks very much, Dr. Simone. I really liked it. So I'm Sayed, a researcher at the University of Waterloo. I'm just having a few general questions, if you could kindly answer them. So the first one I'm going to ask is that, so for the thermoacoustic, concept that you were, discussing, I was wondering how much do you think the generated power and the heat by the RF signal need to be in terms of the strength to trigger the transducer for the acoustic part?
Yeah, so I think I see the question here. So what you're asking is that you'd like a good resolution. I think resolution is probably more dependent on the bandwidth. And we don't need a very high resolution because SAR varies fairly smoothly. So you don't need a millimeter, especially when it's 1 gram average SAR, it's all pretty blurry. So yeah, I think what we have here is working well. We have we have 500 kilohertz, 200 kilohertz, both are probably good enough. For the power, I did a study in the paper. I don't remember all the values because I wrote that a few years ago, but I think,
yeah, just out of curiosity, yeah.
The 8 kilowatts of the 70, it actually has 10 kilowatts. It has some extra power. That was enough in the first estimation.
Okay, perfect. So I'm not sure if I have time for asking another question or not. So
it's okay, you can ask. That's fine.
Okay, so I like to see the deep learning part, which was the unit architecture on the SAR. I thought it was developed by Saim. So I was wondering in the decoding arm, how much was the size of the last stage of the unit?
Oh, I have to look in detail. I think maybe 3 layers. That's something that's hard to answer right now, but we could email if you want, and
okay,
I have
sure,
a
absolutely,
conference paper on it too, so you could read that.
Yeah, because I saw a variation of the images at the predicted the images, so probably might be more than, it is 3, I think. Yeah, so if I see it clearly, so the last stage at the right top, so there are 3 classifications there. Okay. Yeah, thank you very much. I really enjoyed it.
Great. The next question from Larry.
Hey, thanks, Simone. I was really intrigued by the stretchable capacitors, and just wanted a couple questions. I think I might have missed. What was the conductor that was used in those coils, and how big can you make a capacitor? How many picofarads can you get out of it? Is it enough to distribute it a little bit around the coil? And then finally, how the loaded unloaded Q of the coil fared.
Yeah, okay. So I think that's a good idea. I think that Eliza worked on having 2 more of these capacitors, so you can have some 2D stretching too, because right now that's more or less 1D stretching. So my intuitive answer would be yes, you can do that, because that almost already covers all of the coil. Yeah. And then for the Q factor, I don't have that written down here, but I think it was pretty good. I can, pull that up for you and email you later.
Okay. And what was a conductor?
So that's gallium. You detected gallium indium. I'm so new to this.
Gallium indium in a little rubber tube.
Yeah. So the material for the polymer.
No, yeah. So the conductor is what I was wondering about.
Yeah, that's gallium indium.
Okay, great, super.
So we submitted to ISMRM. I hope it gets accepted, so then you can read more on it.
forward to it.
Great. If anyone has any other questions, feel free to write it down in the Q&A. I have one short question, Dr. Winkler. So in the third quartile, I think when you mentioned the use of the unit, you've used a model to simulate the SAR. And I'm just wondering, do you think this model will be enough using synthesized data to classify in vivo data, or would you need real SAR maps to augment your learning?
Yeah, that's a very good point. Well, real SAR maps, that doesn't exist in its form. But I proposed some grant work, and what I did there was use thermometry as another data point. So that was one avenue that I can imagine using in the future. In terms of the anatomical image, of course, a real image will be used. It was easier for this first study to mimic the image in some other way just to get started. But yeah, I think that should be straightforward because registration nowadays works fairly well. So.
Great, thank you. And I think we have another question from Bruce Jenkins. Can you please unmute?
Yeah, very nice talk. Unfortunately, I came in a little late, but what I saw was great. What I was curious about is just, it's kind of funny, like this whole idea of, Lorentz balancing to mitigate acoustic noise. That was Peter Mansfield published a paper back in the 90s about that, and they were using ceramics and aluminum. So I'm just curious, it seems like what you presented was pretty much, that same kind of approach. And so what's taken so long?
Are you talking, I think what Lorentz damping and the damping from ceramics is a different thing. So the Lorentz damping is actually intrinsic, and people hadn't really described that yet as much. So when you have a moving conductor in a magnetic field, that causes a countercurrent, and therefore the force that you expect is actually lower than what was mostly described before. But the damping with ceramic liners, yeah, that was definitely thought of. I think some people even suggested things like casting the whole gradient coil in ceramic. I don't know how feasible that is. Yeah, so that's, but what I guess what's new was that we can now really describe this well in simulation. So we have this platform which is a great starting point to analyze all kinds of mitigation of acoustic sound. We did other things too. This is just one example. I didn't want to spend too much time because I have so much to talk about. Right.
Yeah, no, but in that paper, they built gradient coils that worked. They got like something like on the order of 20 dB acoustic.
Yeah, I remember that.
Yeah.
Thanks for bringing that up.
It just seemed like this was very pretty much the same kind of thing. I was just wondering why those coils haven't made it into scanners already, since it's so.
Yeah, that's a good question. I think there are some problems. Maybe it's heavy, it's not great as a material, maybe brittle. So since we haven't built it, I'm not entirely sure. I left the lab at Stanford when I was, around this point. But yeah. Also, I think one reason is that there are just not that many people working on gradients in the world. And I think a lot of people think it's a project for industry. It's not so much a research project. It's more something industry should do. So, yeah.
Right. Okay. Thank you.
Great. So thanks again, Dr. Winkler, for this great talk. We hope you'll get your 70 very soon, and you can invite us to come.
I hope that too.
Thank you, everyone, and thank you again.
Thank you. Thanks so much again for the invitation. I had a great time.
We did too. Thanks.
Bye.